Chapter 7 provides solutions for external flows. External flow means that there is a boundary layer, so an external flow situation outside of a boundary layer, an internal flow inside a boundary layer. These solutions correspond to forced convection as well, as opposed to natural convection. These are not natural convection situations. There's some fan or pump or something causing or providing a flow source. So the solutions are provided in terms of correlations, empirically determined, or sometimes just analytically determined, but they're presented in terms of dimensionless parameters. So this is our scaled heat transfer coefficient, HL over K of the fluid, Reynolds number, U times X divided by nu, and a Prandtl number. Prandtl number is the ratio to diffusivity, so this is nu over alpha. Right, nu is the kinematic viscosity divided by alpha, the thermal diffusivity. The correlations also could be provided in terms of an average H, so this would be H bar times X over L, or I would prefer to call that L over K, excuse me. H bar times L over K. So all of these depend on the flow situation, which can be very challenging to solve even numerically or with computer simulations. It is done that way sometimes. There is a mathematical problem that you actually are looking for a solution. The boundary conditions over a plate, for example, we're going to look at flow over a flat plate first. It's the simplest case. We're either going to assume the entire surface is at the same temperature, isothermal. It's the more popular case, or we will apply a constant heat flux. In reality, it's probably neither of those, one or the other, but the more common thing is to assume an isothermal surface, which basically means that the surface material is made out of something highly conductive, so that the resistance for energy to move along the length of the plate is a lot less than the resistance for the energy to convect out of the plate. We could have cross flow past a cylinder or past a sphere, and all those things provide average heat transfer coefficients as well. So there's all kinds of resources to try to get solutions for these correlations. Theoretical approach for the laminar flow, we'll talk about the Blasius solution to a flat plate. Experiments, even experiments where you go and make measurements, usually also involve an expected theoretical trend or variance, and so the combination of kind of theoretical and experimental means empirical. So for those, the very popular thing to do is just to go run some experiments and come up with some empirical correlations. The way we would do that is put an electrical resistance, so just a wire inside a plate, right inside the object for which we want to know the heat transfer coefficient. So this would be flow past a flat plate. Let's say we have uniform flow coming in this way and parallel over a flat plate. There's a heat transfer coefficient, an average one over the length of this plate. Well, what we could do is heat this plate up, measure the temperature of the plate, measure the temperature of the ambient flow. We also would need to measure the area, cross-sectional area of the plate, and then Q we can measure as voltage times current. All of the current, all the resistance energy is dissipated as heat. So that gives us a direct measurement for the heat. Half of it goes to the top, half of it goes to the bottom. Right, so we can now solve this equation for H. This gives us a nice easy little means to calculate H with some quick little experiments. Of course, then to investigate, we would increase the upstream flow to figure out a new H, right? Maybe change the temperature of the surface, get a new H. So there's many things that you can vary here. Put a different fluid, maybe you put water versus air flowing over that. So then the correlation would be presented in terms of dimensionless parameters. And so all of your experiments for water or different velocities would all combine in a dimensionless, in terms of dimensionless parameters, to a single correlation. So you would just now fit a curve through your data to calculate the best value for M, C, and N in this case, and that gives you a correlation. So this work has been done, and many different correlations have been provided for you in this chapter. And so you just have to be able to identify which correlation is best for your situation and how to use it. Because you may want to come up with H over only a portion of this rather than H bar over the entire domain. Another thing to point out that's very important is when the experimenters do this correlation, right, they need values of the properties. For example, this KF that shows up here, also nu that shows up in the Reynolds number, even that Prandtl number. All of those values, all those properties are evaluated at the average temperature. So the fluid, right, is not at T average over the entire domain, right? Inside the boundary layer, the temperature gets closer and closer to TS until on the surface, the temperature of the fluid is actually TS. So we use an average. That's called the film temperature. The film temperature is the average between the ambient and the surface divided by 2. Add those together. So that takes some time. There's a little bit of an extra burden to calculate this average, then go get the properties. Don't just use T ambient, or don't just not even think about it and go get the properties at 300 as they're so often given to you. You need to go get the value at the particular temperature, film temperature. Okay, so the simplest geometry to look at is flow over a flat plate. So flow comes in parallel to this flat plate and then passes over, causing there to be a heat transfer coefficient along this entire surface. So that heat transfer coefficient, there's also a shear stress along the surface, so the heat transfer coefficient and the shear stress vary along this surface. There's a boundary layer. The boundary layer increases as you move to the right, right? No boundary layer before there's an effect of the existence of this plate. So there's a boundary layer. On the edge of the boundary layer, the velocity is 99% of U ambient. On the edge of the thermal boundary layer, the temperature is 99% of T ambient out here. So there's a thermal boundary layer and a momentum boundary layer. At some point downstream, the flow will transition from being laminar, it will become unstable, and so there will be turbulent flow. So turbulent flow is little gushes and vortices that randomly appear and then dissipate and disappear, and so there's still, on average, the flow is moving to the right, but there are little gushes that are occurring all the time. So now when we make this plot of a temperature profile in the turbulent region, this is an average. So this over here, that's a U bar, right, where this is a U as a function of Y. This would be a U bar as a function of Y down here. So different physics in this region. There's a lot of mixing and advection as energy is carried up as well and down. And over here, there's no advection in the lateral direction, or very little, right? So most of the energy is carried laterally across the flow by diffusion. Over here, there's a lot of mixing, so heat transfer is much improved with all of this fluid mixing that's occurring. There's also a buffer layer and a viscous sublayer. So inside the boundary layer, the flow on average is about the same, so it's fairly uniform throughout a large region here. Even though it's still less than 99% of T ambient, it's still very uniform. And then when you get close to the boundary layer, there's a viscous sublayer where the gradient gets larger down near this surface. So because of this viscous sublayer and this being so sharp, the gradient in this turbulent region is larger than the gradient back here in the laminar region, even though the drawings here don't really show that very well. So the shear stress, which is mu du dy, is going to be larger in the turbulent region than in the laminar region. Also, okay, we'll talk about those later, but also as you move to the right, the gradient is going to decrease as the boundary layer increases. Okay, so this transition to turbulence occurs at a Reynolds number, a value of the Reynolds number equal to 5 times 10 to the 5th. That Reynolds number is your normal Reynolds number, with the exception the length scale is actually the distance from the leading edge of the plate. The distance from tip all the way down to here is this x sub c. So when this is equal to 5 times 10 to the 5th, which means x sub c, solve this for x sub c is equal to nu over mu times 5 times 10 to the 5th. This will end up with a distance units of distance. Right? For x values larger than that, the flow is expected to be turbulent. For less than that, the flow is expected to be laminar. Of course, that's just the general trend if you're not actually engineering and trying to make that different. In the laminar region, the boundary layer, the ratio of the two boundary layers, this is motivated theoretically, is actually Prandtl number to the 1/3. Alright, this is valid for Prandtl numbers greater than 0.6. For air, the Prandtl number is 0.7. For water, it's 7 point something. And so, for many engineering applications, this is valid. Prandtl number is typically large. For air, the Prandtl number is 0.7, so the thermal boundary layer ends up equaling about 1.13 of delta. So what I have drawn up above might be representative of air. The thermal boundary layer is a little bit higher than the momentum boundary layer. For water, the Prandtl number is 7.5. Make substitutions, you'll find out the thermal boundary layer is about half of the momentum boundary layer. So a lot more diffusion going on, carrying the energy out faster. In the turbulent region, however, with all of the mixing over here, the boundary layers are effectively the same. Mixing is dominating everything. So the mixing is dominating the momentum, is also dominating the thermal or energy distribution as well. So they're the same. And then we already talked about that transition. To talk about what we expect to find in the trend of the heat transfer coefficient and the wall shear. Let's do wall shear first, since they have velocity profiles given. In the laminar region, this is u as a function of y, so we're just drawing a profile through here. The shear stress, remember, is mu du dy, so this slope at y equal to 0 is very important. The larger that slope, the more shear. Okay, so the smaller the boundary layer, so if we shrink down this, imagine compressing this shape, the larger shear we're going to have. The smaller the boundary layer, the more shear. In the turbulent region, the boundary layer, this viscous sublayer, creates a larger gradient by comparison to the laminar flow. So the shear stress will be larger in the turbulent region than in the laminar region. And in both cases, the shear stress decreases as the boundary layer grows. Because the boundary layer grows, this gradient is expected to decrease. To talk about the heat transfer coefficient, we can just imagine this as the temperature profile. The temperature profile might look something like this. The gradient at the surface, right, is going to dictate H. H is going to be proportional to that gradient. So the larger the gradient, the larger H will be. So the conclusions we just made for shear stress, we can make the exact same conclusions for H. So in the end, I've drawn kind of what the expected trends would be. The dashed lines are the boundary layers. H, or tau, is going to decrease as you move to the right for both cases. But in the turbulent region, it's going to be larger. Alright, so we have a large H decreasing as we move to the right, and then as soon as you get to that turbulent region and transition, somehow we transition up to a higher H. There's probably research and ways to analyze how we do this transition. I'm just going to, in this class, let's just assume it's an abrupt transition from here to whatever the H value would be now with a turbulent correlation. And then the trend returns that there is a decrease in H and tau as X increases. So all the correlations in this chapter provide that trend as well. You would find that that is actually the case. So for the flat plate correlations, let's just go through a reminder. H bar is the average heat transfer coefficient. So regarding a flat plate, what we mean is what is the average between the leading edge up to some distance from the leading edge, L. If you just say H, we mean what is the heat transfer coefficient at that particular X location. I think I've mentioned to you guys before in the Zoom meeting that I prefer to call this X over here on the H bar, I prefer to call that an L. because it's really an average over a length rather than at a location x. But what they mean in the book is what's the average between 0 and x. So if I call that L, then I still am inferring h bar sub x in the book. Okay, so it's the same thing for shear. There's a shear stress at this point, or there's a shear bar, which is an average between 0 and x. And then the correlations are going to be presented in this form. Delta over x, right, is going to be proportional to the Reynolds number to some power. Thermal, is going to be equal to, thermal boundary layer is equal to this boundary layer times a Prandtl number to the minus 1/3 power. So solve for this one and put it in place over here to get a correlation for thermal boundary layer. Drag coefficient is proportional to the Reynolds number to a power again. And the same thing for the average case, proportional to the Reynolds number to the power. For the Nusselt number, the local heat transfer, scaled local heat transfer coefficient, that's proportional to the Reynolds number to a power, but then also a Prandtl number to a different power. So we have two coefficients, actually 1, 2, 3 coefficients of a correlation to figure here. And you have the same format for a correlation for the average. These would just be different coefficients. Okay, so all these correlations are going to be different depending on if you're in the laminar or in the turbulent region. Obviously, even if you must have a flat plate for these correlations that I'm going to give you later to apply. But there would be similar correlations for flow around a sphere, for example. So you could go look at table 7.1 to look at all the possible correlations that are given there for you for flow over a flat plate and then flow over cylinders, and they're all kind of compiled there in a nice summary for you. I'm going to start talking about where those correlations come from so we know a little bit more about them. And so to start doing that, we need to focus on just one region. So we'll start with flow over a flat plate, the entrance laminar region. There is actually a theoretical solution for that. Blasius worked for Prandtl years ago and around the turn of the century, so 2 turns of a century ago, or early 1900s, he came up with a solution for steady flow, 2D flow over a flat plate. So flow comes in uniformly this way. We're assuming that u is only a function of x as you go down the plate and y going this way. And so he looked for an analytical solution for that and was able to apply the concept of similarity. What he recognized is that if you were to look at a velocity profile here and then look at a velocity profile here, this magnitude change is going to be the same, right? That's 0.99 u ambient. Over here it's 0.99 u ambient. The only thing that's different is this distance, this delta from there to there. This is a larger delta. So he presumed that this shape was exactly the same as this shape, just stretched out as you move downstream. So he was clever and said, let's just recognize this similarity, and I'm going to look for a solution in terms of a stretched y over delta. And ignore the x dependence. The x dependence is actually presumed to be inside this stretched variable because y is stretched by delta and delta depends on x. And so he figured that there would be only one solution in the end if you express the solution in terms of this, which is called eta in his nomenclature. And so he also scaled u by u ambient. And so he went through and converted the equations, the boundary layer equations, which are partial differential equations in terms of the y direction and the x direction, combine that into one variable, one independent variable, eta. So his partial differential equations turned into ordinary differential equations. It was nonlinear, but he was able to solve that numerically. And so that's called the theoretical solution for laminar flow over a flat plate. That's the Blasius solution. With the Blasius solution, it's easy to use that to come away with what the correlations would be. Just take the solution and put it in the form of the correlations. So the only thing that's going to impact this is actually the flow at the surface. So anyway, we end up with delta over x equals 5 over the Reynolds number to 1/2. So that's a correlation that's provided you. That's the very first correlation, I think, in table 7.1. Remember that Reynolds number, right? There's an x inside that Reynolds number. So there's an x to the 1/2 dependence in this denominator. So if you take this x to the other side, you'll end up x to the positive 1/2 on this side. So delta is actually proportional to the square root of x. Delta decreases as delta increases as x increases. It's proportional to x to the 1/2. For the similar for the skin friction, so the friction coefficient, so this will be the shear stress, is proportional to a constant divided by Reynolds number to the 1/2. So again, this would be nu times x over mu to the 1/2. So whenever you're doing calculations and you need to know what is delta or what is the shear stress, you have to make a substitution for the definition of this parameter. Solve for the shear, for example. So take 1/2 rho u squared to the other side over here, substitute in for the Reynolds number, and that gives you a function for tau as a function of x. For the average case, there's actually an average skin friction coefficient. So the average shear stress scaled by the same scale, 1/2 rho u squared. This is units of stress here, so this will end up being dimensionless. And again, instead of x, I've got an L there to recognize that this is an average. Just like the Nusselt number, this actually is not the average over the skin friction coefficient. This is actually, you have to average this shear. Average shear is the average of this. So you have to do it in dimensional parameters rather than dimensionless parameters for those. Okay, so those are some correlations regarding the flow field. Regarding the thermal field, you can take Blasius solution and apply the same concepts and find theoretically that delta over delta thermal is proportional or equal to Prandtl number to the 1/3 power. We can also come up with Nusselt number correlations. So H times x over k of the fluid. Remember, that's k of the fluid. It's a constant. The Prandtl times Reynolds number to the 1/2 and a Prandtl's number to the 1/3. Be careful about the sign of this, right? Because in the other correlations, that was Reynolds number to the minus 1/2. Here is Reynolds number to the plus 1/2. Then also this is 1/3, so we have a 1/2 and a 1/3 there. So if we scale the average heat transfer coefficient, you get this Nusselt bar. Alright, so H bar is the average of H. Nusselt number is not the average of that Nusselt number. Sorry, I keep saying that, and it still won't be enough. So the correlation looks very much the same. The only difference is the coefficient in front. And if you notice by observation, this constant is 2 times that constant. So it turns out in laminar flow over a flat plate, H bar is actually 2 times H. Alright, so the average H between x equal to 0 up to the location x is actually equal to 2 times the local x at the end. Alright, so at x. So for laminar flow, okay, so wait, there's restrictions on these up above that the Prandtl number has to be greater than 0.6, which in general for most engineering applications that's true. We just looked at air was 0.7, water is 7.56. For most engineering applications, this is going to be the case, and these will be valid. The one exception is liquid metals correspond to low Prandtl number values. So if you're looking at flows of molten material and metals, maybe you're analyzing a weld pool or something like that, then you're going to need to go to a special correlation for these. So this is valid for Prandtl number greater than 0.05 and then up to 0.6. These correlations are given in terms of a Peclet number. The Peclet number is the Reynolds number times the Prandtl number. So if you make the substitution, then you would see that this is actually Reynolds number to the 1/2 times Prandtl number to the 1/2. It's very, very similar to what would be up above, except it's Prandtl number to the 1/3. So they really only effectively change the one term. But it's appropriately expressed in terms of the Peclet number. If you remember, the Reynolds number comes from scaling an average Stokes equation, and the Reynolds number physically represents the importance of inertia relative to that of viscosity. So it's like the nonlinear convective acceleration term in the Navier-Stokes, the magnitude of those terms compared to the viscosity term. That's what the Reynolds number implies. Well, if you look at the heat equation, which looks very, very similar to the Navier-Stokes equation, and scale that, you'll end up with a Peclet number. The Peclet number represents the importance of advection of thermal energy. Right, so that's very analogous to the convective acceleration, the advection term, in comparison to diffusion, the diffusion being analogous to the viscous dissipation term. So it's very, very similar, but it is more appropriate to express this in terms of what comes out of scaling the energy equation. And if you went to look in the literature, this is what you would find. So we need to represent it in that way. There is an attempt to try to come up with a single correlation that applies over all Prandtl number values so that there's no bound on that. So this is the result for that, if that's important. This is restricted to large Peclet numbers, so Peclet number being larger than 100. Remember, the Peclet number is just another dimensionless parameter. Reynolds number times the Prandtl number is the Peclet number. Okay, so I've just given you several correlations. They all apply to an isothermal plate boundary condition. So if you have an isothermal plate boundary condition and H is varying, right? H is a function of X, it varies over that surface, then the heat transfer, so Q double prime, can't possibly be a constant. If delta T is the same and H is changing, then the heat transfer is going to be different. Q double prime, the flux, will be different. Okay, so that's one assumption in isothermal plate. We could assume that we have a uniform heat flux instead. So assuming an isothermal plate promotes the development of theory and empirical correlations. It's just convenient to do it assuming an isothermal plate. Assuming a uniform heat flux is another convenient mathematical model that will get us to some solutions. So if we go back and think about what's actually happening on the plate, let me go back and get a picture. This one will do. Okay, so the temperature, we know that H is changing along the length of this plate because the flow solution is changing. So if we assume that this plate is made of a conductive material, then we can assume that all the energy transitioning this way happens very, very easily. We can expect this plate to be all at a uniform temperature, just one big piece of metal at a uniform temperature. And then Q double prime, the flux, then is varying throughout this situation. Actually, it's probably not exactly what's happening. It's probably not an isothermal plate because nothing is perfectly conducting here, but it might be really, really close to that. So another possible boundary condition to impose is a constant flux all the way throughout here. Now that's not practical either. Probably. There probably won't be a constant flux. There's probably going to be more flux in the turbulent region where H is higher than over here. That's what I would expect. However, the flux might be controlled locally. Maybe we can have some varying little heaters to kind of control this heat flux to make it occur uniformly. So it's another situation, another solution for us. For the most part, we would just assume that this surface is isothermal in most engineering applications. So just be aware that there are other correlations that show associated with a uniform heat flux, completely different physical situations, so there's different correlations for that. So the one that the textbook gives you, the real popular one that would be found in any convection textbook, Kays and Crossford is a convection textbook. Looks very much like the other correlations, just different coefficients here. This is valid for Prandtl numbers greater than 0.6. Here's another one I found in another textbook, no Prandtl number restrictions on that one that applies for a constant heat flux. The thing to remember for a constant heat flux situation is that this Q double prime is constant, but remember H is still not constant. H is not constant because the flow conditions are varying from the leading edge of the plate on, laminar or turbulent for various reasons. That's varying. And so this temperature on the surface is no longer constant either. So this is a local Newton's law of cooling then that occurs at every point. So we could solve this equation for Ts. Just do the algebra, solve for Ts. Ts is equal to T ambient plus whatever Q double prime is. Remember that's a constant divided by the local H. So this will be a function of X because H is a function of X. That's a function of X through this being a function of X. So we could come up with the temperature distribution for a constant flux situation. It's kind of difficult now to talk about what would be an average heat transfer coefficient because the temperature is varying. We can't use Newton's law of cooling that says that the heat transfer is equal to H bar times delta T because there is no fixed delta T. Delta T is varying. So we would want to do that in terms of an average delta T. So the average delta T, Ts minus T ambient, or the excess temperature, well, we could evaluate that just by integrate from 0 to L divided by L. Integrate what? Take that T as a function of X and put it right here. And use the correlation to figure out what H is. If you do that work, you'll end up with this correlation for this definition. Now, instead of an H bar, this is the definition of the average Nusselt number. It's related to an average temperature instead of an average heat transfer coefficient. So those are just some of the things you need to be aware of if you're going to deal with constant heat flux. Okay, so before we start working examples, let's talk about the correlations that you have available to you. So each of the correlations correspond to different situations, so we need to consider each of the situations separately, and we'll go through where the correlations come from. First, let's talk. Oh, wait a minute. Did we already talk about this one? We did. My notes got mixed up. We did this. Okay, so I have my notes in order now. My apologies for that. And it is time to work an example. Okay, so let's consider parallel flow atmospheric air over a flat plate. The air temperature, the free stream temperature coming over the flat plate is 300 K. The velocity, upstream velocity, is 25 meters per second, so it's moving at a considerable pace. The surface temperature is at 400 K. Evaluate the boundary layer thickness at a distance 10 millimeters and 100 millimeters from the leading edge. And then it goes on to ask if another surface is installed 3 millimeters higher over here. At what distance from the leading edge of the plate do the boundary layers come together? So if there's a surface up here, imagine that surface continuing on. I just didn't draw it over the entire distance. So it also has a boundary layer mirroring this boundary layer growing. Eventually they come together. And after they come together, if you were to move farther downstream, this would be considered an internal flow. So there's really no boundary layer, so no domain where you're outside of the viscous dominating area. Everything is viscously dominated. So the internal flows are kind of a different situation. For external flows, we think about there being a boundary layer with some physics of the flow outside, inviscid, and then viscous inside the boundary layer. Okay, so we really want to know what is the distance at which this boundary layer grows to 1.5. That was just a tricky way of asking that question. And then in part 2, they're asking for the shear stress at those same locations. And I go ahead and calculate the drag force also associated to those shear stresses. This part is asking for the vertical component of velocity. Just ignore that. That was from years past. I'm not going to ask you guys to know that. You really need to know some more about the velocity boundary layer solution and Blasius solution to be able to solve that one. Okay, so the first thing to do is to check the critical distance to see if our flow is laminar at these locations, these distances 10 and 100 millimeters from the leading edge. So to calculate that critical distance, take the Reynolds number, set it equal to 5 times 10 to the 5th. Alright, that Reynolds number is u times x over nu. Solve for x. X is 5 times 10 to the 5th, nu over the velocity, upstream velocity. For that nu, that has to be evaluated at the film temperature. The film temperature is 350. Go to the table and get the corresponding kinematic viscosity for that. The units of this will be a length, so make sure you put things in the appropriate length or dimensions. The critical length in this case ends up to be about 420 millimeters. And so the questions are referring to x equal to 10 and 100, so well short of this length. So we are definitely in the laminar region, which means we can go get the Blasius solution correlations and use those. So if you remember, this was delta over x equals 5 over the square root of the Reynolds number. Well, I've already done some work, and I've taken that x to the other side and combined it with that Reynolds number. So instead of so we end up with an x dependence to the 1/2. So you need to do that manipulation. So this gives us delta as a function of x, and now you can evaluate this at any location you want. This would be valid all the way up to xc. So we get about 0.46 at 10 millimeters. So what is that? 1/20th of the distance from the leading edge of the plate, and here we have almost 1.5, so 1.45 at 100 millimeters. So still less than 2 millimeters at 100 millimeters from the leading edge of the plate. So the boundary layer is not growing very fast in this case. For the second part of this question, where it's asking for what is the distance from the leading edge until you get to a delta equal to 1.5, take that same relationship, solve it for x, take x over here. And now we can substitute in 1.5 millimeters here. Make sure we follow units appropriately, and we'll come out with 100.7 millimeters. It's the distance from the leading edge until we get to delta equal to 1.5. So this, I actually believe, if at 100, delta has grown to 1.45. If I go a little bit farther and get on down to 107.6, the boundary layer grows a little bit more and makes it to 1.5. So those numbers seem consistent. For part B, to come up with a shear stress, well, we need to use the friction coefficient. The definition of the friction coefficient, that would be the local shear stress. Okay, so it's 0.664 times Reynolds number to the minus 1/2. Take this to the other side of the equation, and that gives us an expression for the shear stress as a function of x. We are going to need that density, so we need to look up the density at that temperature, at the film temperature. But now we can calculate values for the shear stress at those two locations. I really don't have any expertise to validate the magnitudes of these, I guess not for the boundary layer up there either. But at least the trend is observable, and that as we get farther from the leading edge, the shear stress is going down. And the units are indeed a stress, at least a Newton per meter squared for these. Okay, so now to figure out what the drag force is, so what's the total shear over that entrance length? What we would need to do is integrate the shear stress over that length. So this would be the drag per depth in and out of the page, really, right? Because we're just integrating the stress over a length. You'd have to multiply it by a width. So this would be per unit width into the page, right? So we already have an expression for t as a function of x. We can substitute that into this integral. Take all the constants out front. And just integrate this one x dependence and evaluate that from 0 to L. So that gives me a formula to evaluate the drag force, and you do end up with a Newton per unit per meter depth into the bore. So the drag force is larger when you have a longer plate. That makes sense. Even though the shear stress is going down, the total drag that is accumulating between 0 to that point is larger. The rest of this that's here on this page, you can kind of ignore unless you're really interested and you want to get into it. All this stuff comes from the Blasius's solution and his analytical work to come up with a solution for B, which is the vertical component of velocity, not the horizontal component, but the vertical component. And so ultimately, a streamline looks like this. Streamline coming in, sees the presence of the plate, it actually diverts up a little bit. It does pass through the boundary layer, but the boundary layer grows like that, and the streamlines also grow. But that's more of a topic, like I said, for graduate school. Then here we want to be more practical, dealing with calculations. So part 2, let's kind of continue this example. We'll take this same flow situation, call this part 2 of that example, and now we're going to do similar calculations. Let's figure out what is the boundary layer, the thermal boundary layer, at locations 10 and 100. Well, I also have 1 thrown in here too. Then also calculate the heat transfer coefficient. So finally we're getting to a calculation for the heat transfer coefficient, the whole point for this chapter. And then ultimately the heat transfer, total heat transfer by convection through the plate. Okay, so we've already kind of verified that the flow is laminar, right? So here's just that verification again. Here's our correlation to relate the thermal boundary layer to the momentum boundary layer. We've already calculated the momentum boundary layer in the previous example as well. So the connection is that now to get to the thermal boundary layer, we're just going to multiply by Prandtl number to the minus 1/3. Prandtl number for air, you can look it up. This does vary with temperature, but not by much. It's about 0.7. That's just the ratio of kinematic viscosity to the thermal diffusivity, which would be a dimensionless parameter. Okay, so we can solve for delta. If we want to, we can take this delta, substitute it into this expression up here. We can ultimately have a nice little function expression for delta thermal velocity, or thermal boundary layer as a function of x. So substitute in the values of x that we're interested in, 1 and 10 and 100 millimeters. Make sure you take care of the units appropriately, convert to meters there. And so there's the thermal boundary layer. So at 10, remember it was 0.45. Now the thermal boundary layer is 0.515, so a little bit larger as you would expect for air. For part B, we're going to evaluate the heat transfer coefficient. So we're going to use the Nusselt number correlation. All right, so this Nusselt number is h, the local heat transfer coefficient, times x, distance from the leading edge, divided by, this is k of the fluid. Right, so that's equal to a constant times the Reynolds number, so that's to the 1/2. U times x over nu to the 1/2 times Prandtl's number to the 1/3. So if we solve this for x, take the x, solve this for h, take the x and the k to the other side of the equation. So our x dependence here kind of combines to make this proportional to x to the minus 1/2 power, but we can substitute now into this expression any value for x where we want to know the heat transfer coefficient. Remember, we got to go get k at the film temperature, so do the interpolation to come out with k at T film, which is 350. So I've done those calculations, and so here's h in terms of watts per meter squared for h. Okay, excuse me. So notice that it's very high early on, and then it decreases as x increases, as the trend that we would expect. So it's 300, 96, and then 30 far downstream. These are all kind of believable numbers. Convection coefficient for forced air, yeah, it's going to be, 30 to 100 for sure. If you remember kind of our reference numbers that they gave us in the textbook in chapter 1, I think it was. So now let's think about how do we get the total heat transfer through the surface. So let's do this per unit depth. So we will want, what is Q? Alright, so we want the total Q here, but I'm calling it Q prime because it's per unit depth into this page. So what's the total Q over a length, x? So it's h bar times the temperature difference times, instead of an area, we just have this x here. So we need h bar. So if you remember before, I made the observation that the Nusselt number for the average case, so Nusselt number bar, is actually 2 times the Nusselt number, the local Nusselt number. So that means the average heat transfer coefficient is going to be 2 times the local. Right, so the average over this distance is 2 times the value at the very end of that distance. So if I just use that for the heat transfer coefficient, here's the answers I get for Q. So Q, notice that Q, as the area goes up, is increasing. Even though H is decreasing, the total Q over that area is increasing. So here's the H values that are decreasing, the average H values, and here's the resulting heat transfer. I just put it in the form of a little table for you, so you guys need to make sure you can go through and do those calculations. And actually, what I would recommend that you do is you go get the average Nusselt number correlation, and from that calculate this H bar. You will get exactly the same answer, but it's good to have the experience in going and interacting with the correlations. And then down below, I'm not sure why, I've actually calculated the answer at different locations as well. Okay, so that gets us through the discussion of laminar flow. I'm going to go ahead and continue for about 10 more minutes and just talk about turbulent flow, and that'll kind of conclude the same coverage that we managed to talk about during our Zoom session earlier today. Okay, so for the turbulent region, we're now referring to when the Reynolds number is based on the length of from the front leading edge is greater than that 5 times 10 to the 5th. So we're going to use empirical correlations for flow over a flat plate, and that plate is an isothermal plate. So we're just going to take what's provided for us. Delta over x now is proportional to Reynolds number to the minus 1/5 power. So this is very different, not a 1/2 here, but a 1/5, and that constant is 0.37 instead of 5. So drastically different situation for the growth of the boundary layer. The skin friction coefficient is also now proportional to a 1/5 here, a minus 1/5 instead of a 1/2 there, in the different coefficient in front. The Nusselt number correlation is now to a 4/5 power, so that's significantly different. We still have that Prandtl number to the 1/3 showing up there. So new correlations for this is all for local values for these first few that I'm presenting. This Nusselt number correlation is restricted for Prandtl number being 0.6 to 60. So we've already talked about some restrictions in the laminar case where the Prandtl number needed to be above 0.6, and we weren't too concerned about that. Many applications refer to that, but now we also have this upper limit bound as well for this one. But also we have an upper limit bound that the Reynolds number can't be greater than 10 to the 8th. So if the Reynolds number is larger than 10 to the 8th, so the correlation I'm going to give you starts with Reynolds number being greater than 10 to the 7th, so there's a little bit of an overlap, but it still applies. The correlation changes and looks like this. Instead of a Reynolds number to the 4/5, you end up with a natural log times Reynolds number to the minus 2.584. And this is drastically different, but this is the correlation that the researchers came up with and verified would correspond to very large Reynolds numbers. So Reynolds numbers greater than 10 to the 7th and even greater than 10 to the 8th. So use these correlations here until you get up to 10 to the 8th, and then transition to this correlation. Occasionally I give you a reference. Schlichting is a classic fluids textbook, 1969, who is recommending that, and probably has a link to the research that developed that. And, oh yeah, and also remember that the thermal boundary layer is about the same as the momentum boundary layer, which is given up above. So just use the same correlation for the thermal boundary layer. Now the only interesting thing to kind of consider now, if we're going to come up with the average heat transfer coefficient, which is what we need for Newton's law of cooling, now we have a region over the beginning of the plate that's laminar, and then a turbulent region. So if our length of the plate is capital L, as I have it shown here, where you have a laminar region over about half of it, and then turbulent region here, if I want to know what's the average heat transfer coefficient, I have to consider each of the different correlations over their respective areas. So I got to break up my interval, right? The average is the interval So add up h over the length divided by that total length. So we're going to add up h now from 0 to x sub c using the laminar correlation for h. And then we have to go from x sub c to L using the turbulent correlation for h. And you got to do the same thing for the shear stress as well if we're going to get that average. So this gets to be kind of tricky. And so the textbook will call this mixed situation. This is a mixed situation where you have some laminar and some turbulent, and I want to know what that total average h is for the particular length of the plate. So they give you correlations for that. I'm actually going to go through you have the local correlations actually, so you can use those local correlations and come up with your own h bar correlation. But they actually give you an h bar correlation as well for the mixed flow situation. I'm going to show you where that comes from. Take the definition that we just did for h bar. H bar is 1 over L. We're going to integrate from 0 to xc, and this is take our correlation in terms of the Nusselt number, solve it for h. So this is h, which is K of the fluid over X times the Nusselt number. For the Nusselt number here, I'm going to go get the local for laminar flow correlation here. For the turbulent part, I'm going from XC to L. This is H again, KF over X times this correlation. I'll put the turbulent one in here. All right, so I have an X dependent that shows up in here, and an X dependent that shows up in that Reynolds number. Same thing over here. And so we can evaluate these intervals. So I'm going to do that work here. Let's just look at one integral at a time. The first integral from 0 to x sub c. Right, I'm going to substitute in for that Nusselt number. Hang on just 1 second. I'm going to substitute in for that Nusselt number here. Factor out the constants, right? That's a constant, that's a constant, that KF is a constant. I'm going to pull those all out front. Actually, ultimately, those are constants inside the Reynolds number. Those come out front, and I'm left with this dependence on x to integrate. Integrate from 0 to xc, we get 2xc to the 1/2. So take that 1/2, x to the c to the 1/2, combine it back with these, and make it a Reynolds number again. That 2 comes out and kind of doubles that. So there's the answer for the first integral. For the second integral, do the same thing. Substitute in for this Nusselt number. Take all the constants out front until we're left with this for an x dependence. Integrate this. Evaluate from xc to L. So I'm going to have L to the 4/5 minus xc to the 4/5. Now let's do the same thing and take these powers to the 4/5, combine them back with these, and express this in terms of a Reynolds number. We'll end up with a Reynolds number based on L minus a Reynolds number based on x sub c. Okay, so now I'm going to take this for the second integral, this answer for the first integral, substitute back into our expression. There's a common KF. Take the KF to the front. There's a common Prandtl number to the 1/3. Take it to the back. If we substitute in a value of R critical as 5 times 10 to the 5th, these terms combine to be minus 871.32. And so if we make that substitution, then our correlation looks like this. There's our 871.32. Let's take the KF and the L to the other side. That gives us the definition of the Nusselt number, right? The average Nusselt number. And the correlation looks like this. So this is what's found in your textbook for mixed flow. And so this term is what is accounting for the laminar region. So this term, if you remember, is this value because the critical Reynolds number is 5 times 10 to the 5th. If you had a different critical Reynolds number, let's say you somehow were engineering something that tried to make the flow go turbulent sooner or later, then we would come back to this value. Maybe you can make that different, and then that will change this number. The textbook is assuming the transition occurs at 5 times 10 to the 5th to give you that value there. So if you have a homework problem that is suggesting something otherwise, you got to be careful, and you won't be able to use this correlation. You could do all that work over again to come up with the average shear stress and then put that back in terms of a skin friction coefficient. And you'll get that answer. I don't have the work to show you that. So the only other interesting thing to talk about is that a lot of times you can actually force the flow to go unstable early. For example, a golf ball does exactly that with dimples on the surface. If you can somehow rough the surface up a little bit, or put some little perturbance here, so something that sticks out in the flow, you can trip the flow to be like a wake region here, and so effectively make that turbulent. So there are things that trigger turbulence. So in this situation, there is no laminar region in the front here, in which case just go straight to the turbulent correlation for the local heat transfer coefficient and use that. If you need to know what the average H is then over this entire distance, then you need to use this correlation to evaluate the average, right? So if you want to get to, let me go ahead and add that here, if you want to get to H bar, you're going to have to integrate from 0 to L Hx dx, put a 1 over L out front. You're going to have to evaluate that yourself, right? So that's 1 over L, integral from 0 to L for that H. That H would be, let's see, K fluid over X times the Nusselt number based on X. So you're going to take that correlation and put it right there, and then evaluate that integral, right? And then you can take that Kf and that L back to the other side of the equation. So you're going to end up with a Nusselt number based on L, defined as H bar L over K of the fluid is equal to the integral of Nusselt number over X dx from 0 to L. So you can set that up and evaluate that yourself for that situation. The textbook, the answer that they give you presumes that the transition occurs at 5 times 10 to the 5th. Special notes, just remember that this average Nusselt number is not the average of that Nusselt number, it's just a correlation for the H bar. H bar is the average H. So this we just went through on the previous, we just talked about how we would evaluate that. And then we just need to also recognize there's a laminar and there's a turbulent region. Transition occurs wherever it happens to occur. You're going to assume this unless they give you some evidence that suggests otherwise. If they don't, then you're going to have to evaluate the average using the correlations for the local. And so there is some thought that's necessary to figure out what's the average heat transfer coefficient in mixed conditions, laminar conditions over part of the domain, turbulent over others. Okay, so I'm going to actually stop here. The next thing we will talk about is we will work an example that ultimately ends up in the turbulent region. But we're going to look at a case in this example where we need to know what is the average heat transfer coefficient just over some partial region downstream somewhere. So there's a lot we have to figure out. Are we in the laminar region, the turbulent region? Are we maybe partially in laminar or turbulent? And when we calculate the average, we only need it over this small domain from there to there, not from the front edge of the plate. So there's some thinking that's going to be involved here to use the correlations that do start from the leading edge of the plate. Okay, you guys have a wonderful weekend. I will talk to you guys on Monday. Hopefully this has helped.